on a second. Let me create some room. Take a picture. If this is the mid-segment, it's the line that is parallel to the base of the problem, or the triangle, and it divides the other two sides. It bisects both of them.
Yes.
So what's the relationship between the mid-segment and the triangle's third side? This is the third side right there.
Is it that it's equal to half of the third side and is parallel to it?
Yes, both of those. I can't read your answer. What's your answer say? The midpoint?
The midpoint of the hypotenuse is of equal length to all three, equidistant to all three vertices of the triangle.
Yeah, and this has the characteristics of a circumcenter. In other words, well, let's hold on a second. Let me think about this. What's the relationship between the midpoint of the hypotenuse, which is, hold on. I presume what they mean is that line there. Because they say, I don't know what that really means. With the midpoint of the hypotenuse of a right triangle, where there's the midpoint right there. Oh, it's not a mid-segment. Okay, my error. They're not talking about a mid-segment. They're talking about the midpoint. And what is the relationship between that vertice, and that vertice? How come they took off 1 point?
Yeah, I think it was because I didn't label where the two parts were.
And I don't think that it's actually equidistant from the vertex at the right angle. Let me see if I can draw a triangle where that's not true. There's a right triangle. If I draw the midpoint of the hypotenuse, is that equal? I guess it is equidistant from all three vertices. Yeah. Because that is a median.
Yeah.
And if you draw medians, well, it's a little different principle, actually. Yeah, I'm not sure I was aware of this, that the midpoint of the hypotenuse is equidistant from all three vertices. Means that is an isosceles triangle if that is equal to that, and that's an isosceles triangle if that is equal to that. So when you draw a midpoint from the hypotenuse to the vertex, the right angle vertex, you basically create two isosceles triangles, whereas that's equal to this and that's equal to that also. All right.
Okay.
Wow. I really hate geometry problems that require word answers. I don't think that's helpful to anybody. Explain the difference between the slope of 0 and a slope that's undefined. A slope of 0 is what kind of a line?
A line that only goes horizontal.
Okay, so that's a slope of 0. Hold on. So a 0 slope is horizontal.
Yeah.
What's an undefined slope?
A line that only goes vertical.
Okay. Here's the answer to the first part. What lines is each associated with, and how would you recognize them using the slope formula? Well, we've already said what each is associated. That's a horizontal line. That's a vertical line.
Yes.
But how would I get it using the slope formula?
So to get a slope of 0, you would be doing 0 over x. And to get an undefined line, it would be x over 0.
Well, let's talk about slope. Slope is rise over run. If I take my horizontal line, what's the rise between that point and that point?
The rise is 0 over a run of
whatever that distance is, a minus b. But as long as 0 is in the numerator, then the rise is 0. As long as the rise is 0, then the slope's going to be 0.
Mm-hmm.
And for a vertical line, what is the rise?
The rise is whatever it wants to, like anything over 0, and then the run is 0.
Yeah, and if you're dividing by 0, that's undefined, regardless of what the rise is. And I can make the rise pretty much anything here from a number to infinity. And regardless of how far up I go on this vertical line, my run is 0. So when you divide by 0, you get undefined. When you divide into 0, you get 0.
Yeah.
What information can be gained about a polygon using slopes and distances? Let's draw a polygon. Polygon is just, they didn't say a regular polygon. They said a polygon. So let me just draw a polygon. Draw a 5-sided polygon. Okay. Let's put it on a XY coordinate grid. Now, what information can be gained about a polygon using slopes and distances? Wow. What is your answer? You lost 2 points on this one. What did your answer say?
I said a lot can be gained about a polygon using slopes and distances, such as how large it is, whether it has an obtuse angle or right angles, and what type of polygon it is. An example of this is if I have 3 points and all 3 are different distance, then I know it is a scalene triangle.
Okay. That's true. Trying to figure out exactly what they want here for an answer. It's a very weird question. Using slopes and distances. Well, that means we know the slope of each of these sides. I mean, assuming we have to discern something from the slopes and distances, then we must have to know the slopes of each side. That alone doesn't really help that much. I guess in a way it does. You can figure out obtuse or acute angles based on slopes. Notice that if M1 is the reverse reciprocal slope of m5, then you know that's a right angle.
Mm-hmm.
In other words, whenever two lines are perpendicular to one another, they have opposite, reverse, or reciprocal slopes. In other words, if the slope of m1 was 2, the slope of m5 is minus 1/2, assuming that's a right angle. So by comparing slopes, you'd be able to find right angles. And you would also be able to determine obtuse angles.
Yeah.
In other words, you're going to be able to tell that's obtuse because the slope of m1 is going to be, well, I'm sure we can do it. I'm not exactly sure how. And obviously, when they say distances, we have to know those 5 points also.
Yeah.
So if we know those 5 points, then we know the distance between those. In other words, if I know all 5 vertices and I know all 5 slopes, then I can draw that line. I can draw that line. I can draw this line, I can draw that line, and I can draw that line. So what I can actually do is to know the exact shape of the polygon. And that might be the only answer he wants. The exact shape and position of the polygon.
Okay, yeah.
It's the only thing I can think of that he's looking for.
Mm-hmm.
That was the bottom one, right? All right.
Mm-hmm.
This one looks like I can read a little easier. Again, all sentences. I don't believe I've ever seen a geometry test where every answer had to be a sentence. Must be because it's honors geometry. I still hate it. I do not like sentence answers. I can't believe your teacher does either. That means he has to evaluate the sentence and figure out what to award you on it. That can't be easy. Whereas if he gives you a test that has all numbers, just has to look, see if you get the right number, either right or wrong.
Yeah.
Okay, the 3 types of symmetry are reflectional, translational, and rotational. Identify an object about the classroom that has one of these 3 types of symmetry and explain how you know. Well, what object did you say?
So for number 1, I asked, for the first one, I chose the H on the room ID, so the H was had reflectional symmetry.
Okay, hold on. Let's put an H on there, and let's put it, it helps if we put it on an XY coordinate grid. Now, if I make my H just like that, what kind of symmetry does that have?
Reflectional symmetry.
Over which axis?
The y-axis.
And the x-axis.
And the x-axis, yeah.
Yeah, in other words, I can rotate this over the y-axis, and I got the same thing, and I can rotate it over the x-axis, or reflect it, rather, not rotate it, and I have the same thing.
Yeah.
Now, identify an object that has translational symmetry.
Okay, so for that one, I chose, So for that one, I chose an object. I could choose like an object with like a pattern, so like a checkerboard. You could say that's transitional symmetry.
or something like that.
Yeah.
And you're saying that if I translate that, it has symmetry.
Oh, translate. Wait.
In other words,
Yeah,
if I move that whole object that way, then it becomes this.
I think so. Yeah.
Question is, does that object have translational symmetry? I'm not sure, to be honest.
Hmm.
I'm not sure exactly how translational symmetry is defined. I
I
would
think.
assume that it means I'm not sure. It doesn't really have translational symmetry. This one, I don't know what kind of symmetry it has with that one. It looks the same. Looks exactly the same. It's just been translated, and I could translate it to the right or down or a combination of both.
Yeah.
I don't know that that's called translational symmetry. I'm not real sure what translational symmetry is. Hold on a second. Let me see if it's in the back of my geometry book. Oh boy, that's easier said than done. Okay, here we go. This is in the section about freeze patterns. Because believe it or not, it doesn't say translational symmetry in my book. Let me go to the freeze patterns and see if I can figure out what they mean by translational symmetry. I don't see anywhere in this chapter where it talks about translational symmetry. It talks about translation. I'm not sure I know what translational symmetry means.
I think what he likes. I think if I can remember correctly, he had said translational symmetry is like taking, like in the checkerboard, taking one part of the checkerboard and like being able to replace it with any one of the other parts of that same checkerboard.
Okay. Well, let's talk about rotational symmetry, because I know that one. It's an object that has rotational symmetry.
A square.
Not totally. In other words, if I take a square and I rotate it just 90 degrees, then it looks like that. That's not rotational symmetry. In other words, it looks different.
Okay.
But what about a circle?
A circle has rotational symmetry.
Yeah, because if I have a circle, even if I have, let's say, a wheel that's got spokes in it. Now, I can rotate that, and the wheel looks exactly the same, right?
Yeah.
I mean, I may have to rotate it a certain amount. I can only rotate it one of these angles that the spokes of the wheel is at. But if I rotate it at a proper angle, then I have rotational symmetry. It looks exactly the same. To me, that's what symmetry means, is it looks the same after you've reflected it, translated it, or rotated it. Now, the H looked exactly the same after I reflected it. I could reflect it over the y-axis or the x-axis. So the H definitely has reflectional. A circle definitely has rotational. Translational, I can't imagine any object that I translate. It's going to look exactly the same, but it's not going to be in the same position. But of course, when I reflect it, it's not in the same position either. Although that H, you could not tell the difference whether it's been reflected or not.
Mm-hmm.
The circle, I'd be able to rotate this circle and show it to you, and you would know that it was rotated.
Yeah.
As the translational, I don't know. I can't think of what would have translational symmetry. This object that I drew here, I've translated it, but now it's in a different complete position. So it's not the same as the H, it's not the same as the circle. It doesn't look the same after I've translated it. And it doesn't matter how I translate it. I could translate it right, left, or sideways, right or up or down, and it's not going to look the same. So I'm not real sure what they mean by translational symmetry. So I guess we need to go on. No point in us getting hung up on stuff that I don't know.
Yeah. Okay.
How can I determine if a pattern is linear or quadratic?
So you have to check if the pattern is.
It's a much easier explanation. It's linear if each number is separated by the same amount.
Okay.
It's quadratic if each number is multiplied by the same amount. In other words, this, right? If I want a pattern that's linear, I just have to separate it by 2, every number. That's a linear pattern. It's called an arithmetic sum also. But if it's a quadratic pattern, and I want to multiply each number, let's say by 2.
Okay.
And that is a geometric sequence. So that's the difference. I don't know why they insist upon calling them different words. Everywhere you learn math, they're going to talk about arithmetic sequences and geometric sequences. It's insisting that you call them linear and quadratic, which is true. In other words, this sequence would be defined by a square term. This sequence would be defined by everything being added.
Yeah.
That makes this linear. And when you're squaring everything, you're multiplying. That makes that geometric or quadratic.
Okay.
Compare parallel lines and skew lines. How are they similar?
So
You got
parallel. Oh,
go ahead.
okay. Parallel lines don't touch and go in the same direction forever, and then skew lines don't intersect but go in different directions.
Skew lines are on 2 different planes. Parallel lines, I suppose, could be on 2 different planes, but they don't have to be. In other words, parallel lines, this is hard to draw because you have to be able to draw in 3 dimensions, but parallel lines, that's parallel with that. In other words, no matter how far in each direction I go, they never touch. Okay.
Yeah.
This is not skew lines. Skew lines have to be in 2 different planes and never touch. That's a little hard to draw. Let's say I had 2 different planes. Well, if these planes are parallel to one another, then I can have parallel lines that would be parallel to that if the planes are parallel. So you could have parallel lines in two different planes, but you can also have it in one plane. Whereas skew lines have to be in two different planes. In other words, I can have a parallel line like that, and I can have a line like that, but they're never going to cross because these are two different planes. In other words, they're never going to touch. If they were in the same plane, they would touch, but this wouldn't be called a skew line, or those wouldn't be called skew lines.
Yeah.
So the key is they have to be in different planes to be skew lines.
Okay, yeah.
All right. So how do you use congruence? And when do you use equals? What's the difference?
Okay, so you use congruence when you're talking about two objects that are exactly the same and like are, I mean, it could be, so you use congruence when you're talking about two objects that are exactly the same, and then you just use equals when you're talking about two objects that their lengths or measurements may equal, but they may not be exactly the same.
Here's to me what I think the difference is. Those two angles, they're congruent, but they're not equal because I've rotated that one.
Yeah.
So I'm not sure that you can ever use equal, even if I hadn't rotated it. What you can say is that the measurement of that angle is equal to the measurement of that angle.
Yeah.
How he wants you to word it and comparing the two, I don't know. I've described it as best as I understand it. And it's the same with triangles. If I say this triangle is congruent to this triangle, well, they're not exactly equal because this one is translated, right? But they have the same three angles and the same three sides. So they're definitely congruent. That's all congruent requires is same three angles, same three sides, or if you're talking about a polygon, all sides are equal, all angles are equal.
Yeah.
Whereas when you use the word equal, it applies to the measurement of something. You can't really say that this angle is equal to that angle. At best, I might be able to say that that angle is equal to that angle. In other words, if they're exactly in the same spot, same lengths, then maybe I can say they're equal. I'm not even sure I can say that. But they're definitely congruent angles, and the equals is the measurement of the angle is equal. Okay. Is it possible for AJ to be congruent with JN? That would merely mean they have the same lengths.
Yeah.
And J not be the midpoint of AN. So the question is can I draw a picture where it's not true? In this picture right here, it looks to be, well, I'm not quite sure how they're saying J is the midpoint of AN. It's not. And I think I can draw it differently. Maybe. No, maybe not. So those two are congruent. And that is always the midpoint. If I draw a perpendicular line, that's going to be the midpoint of that third side.
Yeah.
So I think the answer is no. Because this implies their distances are the same.
Mm-hmm.
And if their distances are the same, and I draw a perpendicular line, it's going to bisect that angle. That's the question. If they don't really say, in other words, J is really not a midpoint of AN. J is way down here. AN is way up here. So how can I even say that it's a midpoint? I would say no. That you can draw. Is it possible for J not to be the midpoint? Well, this diagram right here, I don't call J the midpoint. Now, if you say you connect J to AN with a perpendicular line, then this point is the midpoint. But I don't think you can say J is. What if I connect it with a non-perpendicular line? Then it's not the midpoint. So I think your diagram proves that you can draw it where J is not the midpoint of AN. I think they were kind of thinking that you were going to draw it like this.
Well, actually, I think that's what the teacher drew. Like, the teacher drew that as an example.
Okay. Had he drawn it this way, then J is the midpoint because that is congruent to that, meaning they're the same distance. But if I put an angle in there at all, the way the teacher drew it, then it's not the midpoint.
Okay.
It is over here, but it's not over there. So the answer, is it possible to draw? Yes. This drawing over here draws it where J is not the midpoint of AN. Explain and include a diagram, and that would be it. That's all you would need over here.
Yeah.
Okay. So we got angle TFG and GFR equals TFR. Okay. I think I can draw that picture. It's got to be F. That's got to be T. And that's got to be G. And then this is GFR. So there's a diagram that says this.
Okay.
And you can see that it is, right? Based on the angle segment addition property, those two angles have to equal the big angle, even if they're not the same. In other words, FG doesn't necessarily need to be a bisector. But still, angle 1 plus angle 2 equals TFR. So that's a diagram that represents the first part of this.
Yeah.
And then it says NTFG is equal to GFR. Now they're saying those two are equal also. What do you know about FG?
FG is a bisector.
An angle bisector.
Angle bisector.
There's a difference. There's line bisectors and there's angle bisectors. And in this case, you're looking at an angle bisector.
Okay, yeah.
Okay. That was actually pretty easy.
Yeah.
Okay, let's go back. Take lower left.
Yeah, I think that's the second part of, I think, the chapter.
Okay.
That was
At least we have some numbers on this one.
Yeah.
I can't tell you how much I truly hate geometry tests. They're all word answers. It's almost like they're using an English teacher to teach math. I don't get it. Math should be all about numbers. Okay.
Yeah.
So you got 7 correct. Okay. In other words, what you figured out, that was a difference of 1. That's a difference of 1. That's a difference of 2. That's a difference of 3. That's a difference of 4. That's a difference of 5. And that's a difference of 6.
Yeah.
And that's all you need to show.
Mm-hmm.
I don't know how you explain your reasoning, but I usually leave that up to other people to explain it. Okay, this one, that's neither, incidentally, arithmetic or geometric. It's just a sequence.
Okay.
Sequences can be all kinds of stuff. They can be arithmetic and geometric, which is usually the only two they teach you in geometry class. But when you get to calculus, you learn all kinds of different sequences. All right. Now the second one. If I try the same logic, let's just see what happens. That's a difference of 2, 4, 8, 16. So what's happening between each number?
It's multiplying by 2 every time.
Yeah, it's a geometric type sequence. The differences in the numbers are a geometric sequence.
Yeah.
Actually, the differences in the numbers on that one were an arithmetic sequence because you had 1, 2, 3, 4, 5, 6. That is an arithmetic sequence because every term is separated by 1. This is a geometric sequence because to get to the next term, I've got to multiply the difference of the others. In other words, the next is 32, which you've got correct. The next is 64, which you've got correct. So you just have to figure out that each of those differences is double the previous one.
Yeah.
That truly is a geometric sequence, and that's an arithmetic one. Not quite sure why he doesn't tell you that, but.
Yeah.
Okay, 8. Do you want me to pay attention to them if you got a check mark, or do you want me to just pay attention to the ones where you got a minus?
I'll probably just pay attention to the ones that I got a minus on.
Okay. Yeah, because obviously you knew that one.
Yeah.
That's an arithmetic sequence where every number is separated by 5.
Yeah.
Minus 1, because the first number is, in other words, if I wanted to complete this sequence, the first number would be minus 1. Right? In other words, have you had this formula? A to the n equals first term plus the common difference times n minus 1. Are you familiar with that?
I think so, yeah.
Okay, well, we could apply that to this, that first one. In other words, the nth term is the first term, which is 4, plus the common difference, which is 5, times n minus 1. And if I solve that, I get 4 plus 5n minus 5, which reduces to 5n minus 1. So I can get that answer, as long as I know that formula, I can get the answer pretty easily.
Yeah.
And I guess the only way you come up with it in your case is that they don't start with 1. If this went 1, 6, 11, then the answer would just be 5n.
Yeah.
Plus 1.
Yeah.
No, 5n plus 4. I don't know. Anyway, you got that one right. So let's look at the next one. See, the difference between 6 and 9 is 3, 5, 7. Oh, that's an interesting sequence. So it's 3, 5, 7. So it's still an arithmetic sequence. I can get this answer by solving this if I know that formula. And that's the only way I know how to do it. So if he hasn't taught you that formula, he's kind of trying to teach it to you instinctively, I guess. I don't know. But let's plug it into this formula up here. Let me erase everything else. Plug it in and you'll see that it's real simple to do it if you use this formula. Once I've established that it's an arithmetic sequence, it's not. This is an arithmetic sequence, but this is not.
Okay.
So, what does that tell us? You put 3n plus 2. How can you check and see if that's right?
Probably by inserting the numbers into the equation.
Substitute 4 for n, and do you get 21?
No.
Okay. So we have to figure out something that gives us 21 when you substitute 4 for n. So I think I can come up with 2 equations and 2 unknowns.
Okay.
Let's see. Let's see if I can do it. The first term, 1 plus 5. Second term, notice, I think this is what he's trying to teach you. If the differences between every number is the same, it's an arithmetic sequence. If the differences between every number are not the same, but grow linearly, like 3, 5, 7, the next one's 9, and so forth, that's not an arithmetic sequence. It's going to require a squared term somewhere. How about this? Sometimes you just got to experiment with a few things. Does that work for everyone? Does that work for the first term?
Yeah.
Does it work for the second term?
I think so, yeah.
Yep. How about the fourth term?
Yeah.
Here you go. With these sequences, sometimes it's there may be a more appropriate way to do this, but the fact of the matter is I recognize that as a quadratic sequence and that as a linear sequence. When you have a linear sequence, you expect the n to not be squared. In other words, you expect it to look like y equal mx plus b.
Yeah.
When I have a quadratic sequence like b, where the differences between each number are an arithmetic sequence, then you know that you're going to need an n squared because it's a quadratic, it's not linear. So I start right off with n squared. And now it's kind of easy because I can figure out that's got to be n squared plus 5. If I look at that, that's also n squared plus 5. That's n squared plus 5. There we go. I've got it.
Okay, yeah.
Okay. Now let's look at C. That is minus 2, minus 2, minus 2. What kind of sequence is this? Linear or quadratic?
Linear.
Okay. Now, I can take two approaches. I know that with linear sequences, I can use this to come up with my answer, that formula. But I can probably come up with it without doing that.
Yeah.
Let's see if I can do it with trial and error. I know I'm going to need an n, not an n squared. Okay. So it's n plus 5 would give me the first term. Doesn't give me the second term, though.
Okay.
So let's try minus n. Then that would be minus 1, and I would have to add 7 to it.
Yeah.
That would give me that term. But the second term, I don't get it. In other words, it's minus 2 plus 7 is 5, and I'm looking at 4. So, let's try minus n.
Yeah.
I kind of like what you did here. He must have written in that 8. Did he?
Yeah. Yeah, he did.
Okay. So, does that work? And I think it probably does. Yeah, it gives you 6, and then it gives you 4, and then it gives you 2. So this definitely works.
Yeah.
And I guess the moral of this story is that the 0th term would be 8, right? So that number is probably always going to be that 0th term.
Yeah.
But let me show you how to use this formula also to solve this one. Because this will do it 100% of the time correctly, and you don't have to do trial and error or anything. So they want the nth term. So I'm going to do a sub n. What's the first term?
First term is, first term would be 6, yeah.
Plus, what's the common difference?
2.
Minus 2.
Oh, minus 2.
Goes down by 2 every time.
Yeah.
Now, so all we got to do is simplify that, and we're going to get our minus 2n plus 8. Let's see, that's 6 minus 2n plus 2. You get minus 2n plus 8 instantly. If you use that formula, you can't get it wrong.
Yeah.
If you have to do it by trial and error, it's a lot harder. And I can only assume that he's wanting you to do these by trial and error. Merely because you haven't got taught that yet. That's usually not taught until Algebra 2. So what they're trying to do is introducing you to sequences and let you try to figure out the nth term based on trial and error. But if you knew the formula for an arithmetic sequence, you'd get every one of these right all day long, as long as you're dealing with an arithmetic sequence.
Yeah.
All right. What's wrong with your answer?
Okay.
On the first one.
It's not reflected properly.
Yeah, what you have to do is, let's label this. The way to do these is to label your points, your vertexes. I'm going to call that A, B, and C. Whatever ends up on the other side is A prime, B prime, C prime.
Yeah.
But the way I get it is I move point B an equidistant over to there. That's B prime.
Yeah.
Do the same thing for C. An equidistant puts it right there. That's C prime. Do the same thing for A, and it ends up right here. And that's A prime. Now connect the three, and you have the reflection. And there's your right angle right there. Well, it doesn't really say it's a right angle, so we don't really know it's a right angle. But that's the way to do it, is rather than reflecting the whole triangle, reflect each point separately. And then connect the 3 points, and that will be the reflected triangle. But to reflect a point is pretty easy. In other words, to